All right.
No, you didn't.
Welcome everyone to the second day of Koli calling. And we all survived yesterday, so that's good. And we're very glad to have our wonderful keynote speaker, Ben Shapiro, give our first talk of the day. This is a keynote for this year. Ben is an associate professor at the Koli Allen School of Computer Science and Engineering, and also faculty at the University of Washington. Ben, thank you so much for agreeing to do the keynote this year. And
yeah,
floor is yours.
Well, thank you very much for inviting me. Can you hear me in the back? Great. Thank you all for coming. It's nice to see such beautiful people and such a breathtaking place, and I feel very honored to be here with you. This is also my first Koli calling, so I'm very grateful to have been given an offer I couldn't refuse to come to the conference. I want to be clear that I hope that this talk is a conversation starter for discussions that we can continue throughout the rest of this event. It is only partially formed. It's the beginnings of some ideas that I hope we can further elaborate together. So with that said, a brief history lesson. In the United States in the 1930s, there was the first wave of moral panic about cannabis use. A film created at that time was called Reefer Madness, and it's gone on to be something of a cult classic. Right now, I think we are gripped by a kind of AI madness. We have industry leaders who are eager to pontificate about the obsolescence of software engineering jobs. We have executives talking/boasting openly about, maybe I'll use my power to pause hiring. And this is leading many people to even question the value of computing education. I don't know if this makes me an optimist or a cynic or some superposition of both, but I think this rhetoric of obsolescence and doom is mostly marketing that's convenient to tech titans who want to justify layoffs or avoid regulation. At the same time, I do think we are at a major inflection point. Advances in AI are changing how we make software, and those changes have large implications for computing education and computing education research. So my aim here today is threefold. I want to offer a theoretical perspective on how we should think about computing and computing education innovation in the age of AI. I want to celebrate the value of change-making theories and practices developed by scholars from Finland, which is graciously hosting this event for 25 years now. And I want to provide some concrete provocations that illustrate the kinds of contradictions that we should be studying and trying to resolve in our work. Right now, I'm primarily seeing and hearing three views on computing education. The first, which I'll call the hypester point of view, says that coding is obsolete, programmers are screwed, the future is vibe coding, and CS education is passé. This is an extremist view. The second is something of a reactionary view, but it's one that I've heard expressed by some very well-respected people in our field, people who win awards at major computing education conferences. This view expresses variations on ban students from using Gen AI. Sometimes these views are tempered, and sometimes they're not. The less tempered ones call for bans on Gen AI use throughout university computing education. Others, oh, we'll just ban it in the first year. Then others have some sort of developmental theory of, well, students need to learn to do things with AI, but without AI before we should let them do them with AI. Okay? And the third point of view, the one that I want to associate with Leo Porter and Daniel Zingaro throughout this talk, but that I think many of us hold and are in fact doing research along the lines of, is that Gen AI dev tools are now fundamental to the practice of computing, and so we should help students learn to use them well. Folks like Leo and Daniel see this as a moment of opportunity, one in which we help students learn more authentic software engineering skills. So as I said, all of these views are in the air these days. I actually think all of them have some amount of merit, though the further to the right, the more sympathetic I am. But I also think all of them are limited. There are many problems with the hypester point of view, one of which being that those who most vehemently express it are those whose economic incentives are immediately aligned with its uptake, which ought to give us a little bit of cause for suspicion. There's also very little evidence to support its validity. So there hasn't been a lot of empirical research actually showing that there's a whole lot of benefits to companies beyond people's perception that they're more efficient or more productive, actually showing that they are. I don't know how pervasive this is, but I'll say that computer science graduates from my university are finding jobs just as quickly as they did a year or two. We still can't take as many students as want to study with us. And furthermore, and perhaps most importantly, I think most of us here know that coding has never been the hard part of computing. Specification, even understanding your problem domain, is much harder. And we're not at a point where this really speaks to that. I also think the reactionary point of view is fatally flawed. It assumes our learning goals are static. The ideas that computing students should learn are unchanging. I also think it's inauthentic to students' motivations, their existing experiences with technology, and computing as it's increasingly practiced outside the world of schooling. It's also at odds with at least 60 years of research on literacy development. So I don't have a lot of sympathy for this point of view. As I've said, I have massive admiration for the work that Leo and Dan are doing. I think they're two of the most essential leaders in computing right now. And I agree completely with their goals, but I don't think they go nearly far enough. And that's not just a critique of them, it's a critique of the state of our field. So, as an editor, an associate editor, a senior program committee member, and blah, 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 I review a lot of papers. And this critique applies to much of what I read. We're recording the talk, so don't feel like you need to take a lot of photos. For much of what I'll discuss today, I'm almost using them as a straw man, but there isn't a word in English, I don't think, for like straw man that I adore, you know? Um, what I mean by that is I think they're leading the field. So to the extent that I point to limitations in their work, you should think of them as a proxy for the best of what I think we're doing in our field. And so it's a critique also of the field more broadly, right? So to explain what I think they're missing and where I think we need to go, I need to actually explain the title of this talk. So the talk is titled The Coin Has Three Sides. So I want you to imagine this beautiful Finnish euro coin. And then I want you to like mentally rotate it a little. You're computer scientists, so you're good at mental rotation apparently. So you rotate it a little bit more. And then we'll extrude this coin to make the fact that it's a cylinder a bit more clear. All right? So this coin represents the tools, the objects, and the practices of software engineering, of making software. So on one side, we have programs, software, the thing that many of our students are striving to learn how to construct. On the other side, we have programming tools, the varieties of languages, editors, compilers, runtimes, documentation, and other resources that students use to make software. And finally, the third side, the skinny rim of the coin, it's the practice of software engineering. It's the human action that uses tools to construct these programs. And I'm going to argue to you that the reason our shared discourse and our change making around AI and computing education is currently so muddled and so nascent feeling is that we've not adequately conceptualized how all three sides of this coin are changing. And so we've not yet developed coherent theories, models, and tools for what computing education should be in the future. So I'll explain that, and then based on that critique, I want to propose how we should go about understanding these things and working toward collective visions of what future computing practices and computing education, and finally computing education research should be. So to understand how all three sides of the coin are changing, it's helpful to think about advancements in applied AI in three eras. So the first is programs with AI inference. This is like the longest running era, at least from the 60s through to today. The second is Gen AI tools for developer support. And the third, I'd argue, is programs where we create functions by embedding prompts within our code. So you're probably familiar with the first two, but in case you're not familiar with what the third looks like, you can do things now like write code like this, where I can write the header for a function, but not write a function body, and instead embed a prompt that describes in natural language what this function should do, and then I can call it as if any other function. These prompts get interpreted at runtime when I call functions like dutify, in this case, right? So I think that changes in A and B are necessarily changing our practice of C. These are deeply intertwined. And so we need to think very carefully about how all three are changing in order to understand the confusion that many computing educators, computing students, and policymakers are experiencing right now. We're changing what programs are, we're changing what programming tools can do, and we're changing our expectations about what we could or should do with these tools, all of which has implications for what we imagine people should be learning and learning how to do, learning how to make sense of what programs are and what programming tools can do and how they should best apply them. So delta A plus delta B leads to delta C, but also we have this sort of this profound continuing uncertainty about what learning A, B, and C should be. So I live in Seattle, but I am in fact a Californian. Since I'm here in Finland, I wanted to ground this keynote in what I think is the most important academic product of Californian Finnish fusion, which is cultural historical activity theory, or CHAT. So my plan for today is to further deconstruct and theorize the contradictions that define the present moment. I want to propose a concept called human AI software engineering and call for a collective program of expansive learning to figure out what that concept can mean in practice, including educational practice. And to do that, I want to highlight some as yet unmet needs to support the practice of HAISE that I hope will inspire some of you to build new technologies, launch new programs of research on learning, and for all of us to collaborate with each other, with educators, with students, and with other stakeholders to work toward this HAISE concept, or at least to come up with a better concept. So let's dive into theorizing this space. First, I kind of want to tip my hat to the many scholars whose work inspires my own. Engstrom, Lave, Cole, Garfinkel, Flavierg in urban planning, Latour, Hutchins, DeSessa, and many others. I said before that I'd be calling for us to undertake an ambitious program of expansive learning. I know not everybody here is really immersed in that literature. So what does that mean? Well, Engstrom describes it as a process of concept formation. Well, what's a concept? He cites my friends Rogers Hall and the late Jim Greeno, who wrote that concepts and their meanings develop and evolve in settings of practice and are maintained in practices because they're useful in conducting the community's activities. Concepts are the organizing frameworks we use to think about what we do together, the tools we use to do it, and what the purposes of our activity are. And today I'm going to be speaking of multiple communities that have multiple intertwined concepts. So the concepts and meanings that those different communities develop, apply, maintain, and transform. I'm going to focus especially on the relationship between software engineering communities, and computing education, because they're two distinct but intertwined communities. Much of what we do in university-level computing classrooms is about preparing students for participation in software engineering communities of various sorts. And historically, research on university students learning programming has been a big part of Koli. So I chose to contextualize this talk within undergraduate software engineering education, but I hope that the theoretical framing and the argument about how we should act on it has much broader relevance, and I hope that relevance will be obvious by the end of this talk. So Engstrom uses the term change laboratory to refer to structures for consensual, intentional, and collective change making. And I believe that one of the most powerful things we can do right now, not just because of where we're at with AI and computing, but because we're in this moment of rising global authoritarianism, the most important thing we could do is to work together to intentionally, purposefully, consensually construct partnerships with educators and students and with each other to create healthy change laboratories where we invent the future of computing education with AI. So what does it mean to work through change laboratory agency? Well, when we have this kind of agency, we work together to take actions like criticizing existing activities and organizations. We sometimes resist interventionists, including managers, policymakers, or others. We work together to explicate new potentials or possibilities that we see for our activity. We envision concretely what those new patterns or models of activity could be. We make commitments to each other to take actions to change that activity in ways that we find mutually desirable, and then we follow through on those actions to change the activity. Unfortunately, there's also a very particular view in American ed tech circles that educators and educational institutions are woefully out of step with the world. There's the belief that the overriding purpose of education must be workforce preparation. There's little regard for philosophy, theory, or practices that don't support immediate industrial needs, and anti-labor action is a big part of that ethos. And so if that's your view, then why not do everything you can to be as disruptive as possible, to sort of move fast and break things in the realm of education? Why not encourage students to use your Gen AI tools as much as possible, as soon as possible, give them cloud credits, maybe even deny faculty those same cloud credits like companies like Cursor do? Because after all, that is a way to resist the cranky managers, AKA educators, that exist in the world and advance your agenda. So it's a kind of agency, but it's not change laboratory agency. What I appreciate so much about the work Leo and Dan are doing is that they're not only thinking carefully about pedagogy, but they're doing it in a way that looks a lot like change laboratory agency. So if we think about all the things that they're doing in their work, they're criticizing limitations in existing pedagogy, given the evolution and all those sides of the coin that I mentioned. They're very carefully developing new pedagogies, testing them, iterating on them, etc. They're explicating new potentials and possibilities. And let's look at one of the new concepts that they've developed in that vein. Read, critique, and improve is one of the pedagogical concepts that they use and they describe in their textbook. So in it, students are given code and a co-pilot explanation of that code. So there's some code here that, prompts the user to enter your age, and then there's this if-else ladder that, if age is less than 13, print you're a child, else if age less than 20, print you're a teenager, so forth. Then there's an explanation from Copilot of what this code does. But then there's the call to action for students. It says, it turns out that the explanation from Copilot is incomplete in that it doesn't describe the code for all inputs. Determine what the explanation is missing and add your answer to the explanation. So this is but one of many different activities that they describe in their book. And each of these activities has a different concept, but all of them are consistent with and coherent with the macro concept of scaffolding thoughtful and productive use of Gen AI within education about the practice of programming and the practice of software engineering. And so when we read their book and we read their work and we look at their collaborations very closely, we see all of these aspects of change laboratory agency within our own field in the practice that some of our esteemed colleagues are doing. And I think that's something we should admire, even while, as I said before, they don't go far enough. And I think that's because we need to reconceptualize software engineering and computing education and bring them into stronger connection with each other. And doing that requires us to carefully consider all three sides of this coin and where it's headed, right? How the coin is reshaping and how we are in turn reshaping it. So we need to think very carefully about what A, B, and C have been historically. We need to carefully examine how A, B, and C are all changing and evaluate whether and how those changes are actually desirable. We need to develop our own visions and develop consensus around visions of what the futures of A, B, and C should be. Not treat these as things that are determined by somebody else, but see this as a space where we're agentic on all three sides of that coin, which means we need to envision new concepts for software engineering and for computing education in relation to the future A, B, and C that we desire. And I believe that this collective project needs to not only attend to student learning, but also faculty learning, hobbyist learning, workplace learning. And it should involve collaboration with open source and industry projects that build tools for the future of software engineering. So expansive learning is about constructing interventions in socio-technical systems. Interventions are purposeful actions by human agents to create change. In expansive learning, they include the development and reification of new concepts in activity. What I'm proposing is that we think, talk, and act together to construct interventions in the practices of computing education research, and software engineering, and that these should be, and in fact, must be informed by what we know about how people learn, the social values that we hold, and our technological expertise. Now, often when people speak of interventions, they refer to linear processes where you know your goals up front, where the subjects of your interventions, ideally just do what you tell them. And if execution is fraught, then it's a design problem and you just solve it through iteration. You seek maximum generalizability, which means you try to standardize solutions. And as researchers, we love to control variables, but that's not what I'm arguing for here. I'm arguing for what Engstrom calls a formative intervention. And that means interventions where stakeholders work together to describe, to analyze, develop some shared understanding about what's problematic or contradictory about their situation, and where they work together to construct novel concepts, ones that are not known or fully formed by researchers ahead of time. It means working together to figure out how to enact those concepts together, and researchers giving up power to practitioners. As we do so, it's important for us to recognize that formative interventions are contextual. They're not universal. Their adaptability should not be assumed, and it's not even necessarily desirable. So our research methods should not sort of push us into a corner of reducing what we study to things that are easily made portable, as tempting as sometimes academic incentives make that. In other words, this perspective is very hard to reconcile with methods like randomized controlled trials or pre-registered studies or other things that are favored by some in our field. But when we work this way, what we're able to do is collaborate with practitioners to generate new concepts and to build shared agency. And our responsibility is to both provoke and sustain transformations and to uphold practitioners' agency throughout practices and processes of intervention and change making. So next, what I want to do is analyze specific contradictions that computing educators and software engineers are grappling with right now. I want to propose potential concepts for how we should think about the aims and mechanisms of learning, but especially doing software engineering. I want to demonstrate some possibilities for ways new tools could help us to realize those concepts. I want to touch on potential obstacles, but I want to get us all excited about what potentials could exist if we undertake formative interventions to realize these concepts in practice. And as I said, by doing this, I'm not trying to give you some, simple answer that you could take away and use tomorrow. Rather, I'm hoping to provoke and catalyze some form of sustained joint work where we seek expansive transformations of computing education that include reimaginations of software engineering. So let's start diving down our rabbit hole of contradictions. We've already heard a bunch about the first one, which is that Gen AI can do a lot of the assignments we're used to giving our students. I don't think this is a surprise to anyone in this room. So historically, when we've given students homework to do, they've created or modified programs by using tools like assignment specifications, text editors, compilers. Maybe they've even gotten feedback along the way from auto graders. And the objective of this work was to produce a correct program through problem solving, that this problem solving actually was the thing that supported learning. It was included, so the objectives were problem solving, creating correct programs, learning, generating greater self-confidence, maybe also getting a good grade, depending on where you're at. But the contradiction we're wrestling with is that in a world where students have the same assignments, but can make use of AI tools that can just trivially do those assignments, they may be able to produce correct programs, the ones that would have gotten them good grades, but we're skeptical that learning is happening, and we're skeptical that, self-confidence is developing. There may even be a paradox there, as we see in some of the Prather work, where one may develop independent of the other. So we need to understand this by looking at multiple activity systems in relation to each other. So the figure on the right is the mirror image of the one on the left. And when we have activity systems that interact with each other, it's really important for there to be coherence, particularly around what the objectives are. So let's think back now to the Porter and Zingaro work I mentioned before, and why I like it. Well, one reason why I like it is that it offers us a way out of this contradiction by transforming the object and the tools of the activity system of the homework, right? So their concept provides a way to bring educators and students' activity into greater alignment. They expand our learning goals to include things like careful code reading, code explanation, and the development of AI literacy. And by doing so, they create a frame for the subjects on the right, teachers, to begin again to be able to stimulate and evaluate student work for its desirable properties, which we believe are linked to transformations like learning. Now, the student work looks quite different in this redesigned activity system, this sort of read, critique, and improve system. So on the left, the student, the subject, works to produce explanation corrections by modifying the teacher-prepared object of a faulty explanation. And they do so using practical literate skills and the narrative of a fictional scenario, which serves as a mediational resource for them to do this work, the transformation of the explanation from an incorrect one to a correct one. And so through this transformation of these interlinked activity systems, the objectives of students and teachers are aligned. But this happens through the simultaneous expansion of the learning goals and the redesign of the student activity around those roles. This also better aligns the work that both students and teachers are doing to the outside world of emerging software engineering practices. So we now realign what's happening in this learning space to the outside world, rather than the sort of ban it strategy, which actually is about creating greater distance between what happens in classrooms and what happens in the outside world. This remediation reflects a transformation of the mediating artifacts used, as well as the objects that students pursue with those artifacts. So it brings Gen AI into the set of permissible and necessary programming tools, and it adds to the repertoire of software engineering practices that we expect students to learn, including skills like evaluating the quality of Gen AI outputs, verifying the conformance of specifications and code to each other, and improving the quality of written explanations of program behavior. It also probably increases the amount of time that students spend learning to read code, which many of us have held as goals for a long time, but not always there so much in teaching practice. So if we go back to this table that I showed before, we can see the Porter-Zingaro work as a kind of formative intervention. I don't know why I can't say that. Responding to the contradiction by introducing the new concept of programming with AI and teaching and learning practices aligned with that concept. They introduce new tools to the existing educational activity systems. So the sort of officially supported use of Gen AI, reading and rewriting explanations of code. It has to grapple with a potential obstacle, which is that students might do worse in this new pedagogy with respect to previously established learning goals, which, itself begets a bunch of research questions and opportunities for study. But it also offers the potential for helping students to learn productive uses of Gen AI that don't compromise their ability to enact essential software engineering skills. So it improves the learning of computer science by bringing learning into greater alignment with emerging practices for software engineering in the broader world. Now, I've talked about this example a lot. I hope it doesn't feel too belabored to you. But I'm going to gone through this slowly because I wanted to make sure we have some vocab in common as I move faster now. So the second contradiction is that programs are not what they were. So not so long ago, a program referred to a bunch of text, and programs were compositions of symbolically defined functions, procedures, and other values. But now they're hybrid compositions, weaving together symbolically and statistically defined functions. Karpathy refers to these as neurosymbolic programs. I'm just going to call them hybrid programs. But the key thing here is to recognize that our longstanding historical sense of what a program is contradicted by advancements in machine learning. So returning to our coin, we think about what is a program. Well, a hybrid program is not just code, but it's also models, it's also data, and it's also prompts. These are new atoms that we've invented to co-constitute the molecules of hybrid programs. And our research on learning needs to reckon with the new kinds of molecules that new programs are, and that students need to learn to make and understand. So just to work through some examples of what these things mean, many of us probably have phones that we can unlock with our faces, that. So here's a bit of code that might be used as part of the implementation of that kind of security feature. What's really important here is that the called function, faces allowed person, isn't necessarily a symbolically defined function. It might be one that's machine learned. That is, it's defined using statistics, not with symbols, making this a hybrid program. If we look at more code for this program, we might notice a bunch of interesting properties. For example, our program both uses and creates new machine learning models, fine-tuning an existing model with data. Some of those data are available when we build our system, but as we'll see, others only exist at runtime. So there's some, all kinds of higher order functions and dynamism, metaprogramming happening here. And this is increasingly a part of how we build software. Finally, as I mentioned before, programs might also be hybrid in the sense that we can now intersperse function definitions that we write ourselves with functions generated at runtime by prompts that we embed within our programs. So in this code, the describe weather function is defined only with a signature and a prompt on lines 3 and 4, but it's called on line 6 as if this were any other function. And that's new and interesting and messy, and it has many interesting implications for computing education. So for all those reasons, I'm going to slap programs are hybrid up here as a contradiction. It's a historical contradiction. But as I'll now discuss, it's also a pedagogical one, which is that today's programming pedagogy scarcely addresses hybrid programs. So when I look at the pages of TOS, CS Education, the proceedings of ICER, Koli calling, other conferences, it seems to me that in a few short years, we've done much more research on how to help students make small ML models like image classifiers, or on how to use Gen AI dev tools, than on how to help students make and think about programs that are these hybrid compositions, that have these various forms of AI embedded in them, co-constituting a program along with code. The latest curriculum guidelines developed by our professional societies for higher education in computer science and software engineering don't address this hybridity. To some extent, this is reasonable. The software engineering guidelines are over a decade old. We can forgive that. But the CS guidelines were published last year when many of the trends discussed here were already well underway. So programs are hybrid, but by and large, programming education and software engineering education are still very much operating in this symbolic frame. So there's a gap there, a contradiction between educational practice and emerging software engineering practice. I think the fourth contradiction is material, which is that today's development tools are really inadequate for working with hybrid programs. So developers who want to use state-of-the-art editors to mediate their transformations of hybrid programs quickly find that they cannot meaningfully represent or aid in the transformation of the information embedded in those programs. So here's an example. Returning to our face authentication example, imagine I'm trying to debug this system because it's making the wrong inferences. So I set a breakpoint, and now when someone tries to authenticate, my debugger pauses, and I want to use it to do what I usually do with a debugger. I want to understand what's going on in my program. So I usually do that by stepping into the call stack and examining the code in relation to the system state. What's on the heap, what's on the stack. But if I step into this code, I very quickly and almost immediately end up in a place with no useful information. It's not useful for me to see the PyTorch inference code. The level of abstraction here is completely useless, right? It's not helpful to me unless I'm inventing some new model architecture. Seeing a giant array of model weights and input activations, it's not something that's useful. And this is why today's dev tools leave people stranded when they want to debug hybrid programs, even while programs are becoming more hybrid. They need to offer representations of system state or program definitions, including statistical program definitions, in interpretable and actionable forms. Right now, they can't help you to understand why you're getting the predictions that you're getting, which makes them pretty useless. So later in this talk, I'll make some suggestions about research we could do to try to overcome this challenge. So that's the last of the contradictions I'm going to enumerate today. I have a list of more, but time is finite. We can talk later. These contradictions have not been well addressed in computing education research. And I think they're also poorly addressed in computing education practice. This contributes to the current sense of tension that we're feeling between computing education and changes we're seeing in industry and in open source software development. But at the same time, it circumscribes an enormous and exciting research space for us to delve into together. So here's some things I think we should do about it. Now, returning to this sort of framework for formative interventions, I hope I've offered at least a provisional analysis of some of the contradictions. So what I want to do now is describe the germs of a novel concept that I hope we can further construct together, along with educational partners and with students. So the unfinished concept that I want to propose to you is called HAISE, Human AI Software Engineering. And it draws inspiration from Licklider's classic work on human-computer symbiosis. So I'm going to just read what he wrote and published back in 1960. So he wrote that present-day computers are designed primarily to solve pre-formulated problems. Many problems that can be thought through in advance are very difficult to think through in advance. They would be easier to solve, and they could be solved faster through an intuitively guided trial and error procedure in which the computer cooperated, turning up flaws in the reasoning or revealing unexpected turns in the solution. He quotes Poincaré and says, the question is not what's the answer. The question is, what's the question, right? Coding has never been the most important part. It's knowing what questions you need to ask and be able to answer about the domain and what a satisfactory solution would be. So in conceptualizing what he calls man-computer symbiosis, I'll just call human-computer symbiosis, he says one of the main aims of human-computer symbiosis is to bring the computing machine effectively into the formulative parts of technical problems. And that's what I'm interested in. HAISE is a vision of human-computer symbiosis for computational problem solving, for humans and AIs working together to design, create, test, and improve hybrid programs. So if we go back again to Leo and Dan's example and think about what they're having students practice, it's actually a crucial skill for enacting Licklider's vision. If you're going to cooperate with a machine, then ideally both you and the machine would be responsible for identifying flaws in each other's reasoning. The read, critique, and improve structure calls on students to find such flaws and to correct them. So their innovation, it's not just a model for how to teach programming with AI, It's an example of how we can develop people's skills for human-computer symbiosis, for HAISE, for human AI software engineering. So to me, the technical advance that's made 2025 distinctive has been the explosion of agentic software development tools. I assume a lot of people here have played with them, but maybe not everyone. So here's a snapshot of a single interaction I had recently with Cursor. So to give some context, my students and I have been building tools that allow teens to customize image generators, sort of adjusting the implicit defaults in these systems to better reflect their identities and communities. Every image I generate is expensive, in total. And I don't want the cost of this to go beyond my budget. So I asked Cursor to help me to implement rate limiting. So I wrote, I'd like to rate limit users to no more than 5 image requests per minute. Seems generous. With the exception of those used in evaluations, it's a feature, don't worry about it. Create a plan to add rate limiting to the application, including additions to the UI to communicate to users what's happening if they're getting rate limited. I thought it was pretty good. Here's just the beginning of its response, which you could scroll through. It asked me a series of questions that helped me to clarify my goals, as well as my implementation preferences. It wanted to know about the scope of rate limiting. It wanted to know about what kinds of requests should count towards limits and not, and so on and so forth. Many of the questions it had were about things I had not thought through in advance, and probably would have required me to go back and do a whole bunch of refactoring once I hit them as problems down the road. So to me, this is a great illustration of how we're starting to inch towards something like Licklider's vision. The agent helped me to formulate what my goals even were. It helped me to understand more completely what the problem was that I was trying to solve before I actually spent a bunch of time writing code. So that back and forth is one exchange in the kinds of HAISE experiences that I want us to create and that I want us to investigate what learning about can be like. So if we look at this through the lens of chat, we can begin with an activity system where I, a programmer, use the agent as a tool to mediate my transformation of the object that is my program, including its prior specs, its documentation, etc. I act on the agent by giving it directives, create a plan to do blah, blah, blah. And then agency shifts to the AI, which acts on its input. The objects of my work mediate the agent's action, which ultimately is the transformation of my directive into a proposal back to me, the developer, about the future possible specs, code, and documentation that the agent could help me to create. The back and forth of these interactions means that HAISE is a recursive cycle through which humans and AIs together enact processes of engineering hybrid programs. So let's see what this cycle could be like in greater detail as we revisit the examples I shared before. So we'll start with our face-based authentication example, and then revisit programming with code and embedded prompts very quickly. So in both cases, we're looking at hybrid programs. So hopefully you remember this line of code from earlier. Think for a moment about whatever your favorite IDE is, and ask yourself, how would my IDE help me with this program? So right now, the answer is probably not very much. As I said, this function actually calls a classification model. And I want more. I want HAISE help for program writing, program testing, and program debugging, not just for classical programs, but for hybrid ones. So let's start with program writing. If we look at this code carefully, which you don't have time to do, we might notice that there are at least 3 unbound symbols: base face model, negative faces, and faces of allowed users. As I pointed out before, one of these is meant to be a reference to a pre-trained model. 2 are meant to be references to data sets. 1 data set is pre-populated at build time, and the other is only populated when the application is first run, like when I set up a new phone. So the life cycle of data and models in this system is pretty complicated, despite its brevity. The programming tools of the future should be able to help us to define these entities correctly, both in terms of their types, but also their life cycles and relationships. Future IDEs should include agents that have intelligence about these things, and ask developers questions that help them to properly formulate their programs. Those interactions could be chat style, like what we see in Cursor today, or they could be more like traditional user interfaces. Here my IDE has noticed that it seems like I want base face model to refer to a pre-trained model, but it's not bound to anything. So it asks me whether I want assistance with importing a model and binding the symbol to it. So imagine I say yes to it, and I point my editor toward a pre-trained model. Maybe it's already on my computer, maybe it's on Hugging Face, maybe it's even an open model, so it comes with references to the data used to train it. The IDE might also notice that I have an unbound reference to what's probably a data set. Ask me whether I want to create a new data set entity and bind the data to that symbol. I do. Yeah, cool. And once I do that, I should be able to interact with a visual representation of that data set. I should be able to document its purpose in plain English. It's a set of negative faces. It's a set of pre-known faces that are not the owners of the phone. And I should be able to interact with this data. I should be able to interact in machine learning processes by doing things like dragging and dropping sets of face images to it. So for each person in my data set, I should have one or more photos. Now my Smart 8 IDE feels like, it's on a roll. So it offers the same invitation for faces of allowed users, but this time I'm going to say no. And that's because, as I said, faces of allowed users will eventually, at runtime, be a set of images of the owner of the phone, but I don't have those at build time by definition. So the prompt by the IDE nudges me, oh, I need to more fully specify what this symbol is. So perhaps I right click it and tell it to create a runtime data repository and bind it to that symbol. So now I'm starting to have enough of a program that I need to start making sure I have tests for this system. Well, we've written enough of a program definition that my intelligent IDE can draw my attention to an emerging problem. It highlights some text it wants to warn me about, and if I mouse over that, it'll say like, hey, you haven't written any tests that cover this use of runtime data. Well, okay, I'll define a test. And when I choose to define a test around a dataset symbol, my editor reveals it has further smarts about machine learning testing practices. So through static analysis alone, it's able to observe that faces of allowed users is used to fine-tune a new model called trained face model that takes an image as input and predicts a Boolean output. The following definition of face is allowed person is the only place that trained face model is called. Now we're treating models as functions, right? So we can call them. And through basic type inference, it can deduce that photo will also be an image. So it proposes that we define a test strategy that involves the combination of faces of allowed users and photo. And from there, it gives me some options, and I have to make some decisions. How should my test suite evaluate the correctness of a prediction? And what data should the test suite use? Remember, faces of allowed users is empty at build time, so it's going to be empty when I run my tests. It's data that my users are going to provide, which means right now it's an empty set. So my strategy, my testing strategy, is going to be to sample one of the people from my set of negative examples and use it as a positive example, as the face of someone who should have access. This is called cross-validation. So first, let me tell the system the condition that I want to use to decide that a test passes. I want to check that someone who should have access does have access. And now, since I've decided not to make a dedicated test set, but instead to sample from a set of negative examples, I'll tell it I want to cross-validate. And I can provide information about how the cross-validation would work. And now, when I run my tests, my system might create 50 different fine-tuned models by sampling different people from the data set I created, using each of those sampled examples as the allowed users for each of those models. And then each of those models will get tested once by evaluating whether one of the images is the allowed user that was not included in the training set, whether they get authorized, and whether I meet my threshold of good enough. Test passes. Okay. So once we do that, we've addressed this warning. Our test might not pass, but at least we have some test coverage. All set, right? Not quite. We have a problem. So remember what Licklider wrote. We want collaborations with computers that can turn up flaws in our reasoning. Fortunately, in this imaginary future, my intelligent editor can do this, and it catches a flaw in my reasoning. I described a test for when authorized users do get access, but I never created a test to check that unauthorized people are denied access. So my IDE will highlight this symbol and it'll tell me about this mistake in my reasoning. But because I've already generated a plan for how to test for authorized cases, I've given the system a lot of information it can use to automatically generate tests to cover those other conditions, which maybe I'll edit. Maybe I want a higher F1 score because I'd rather not grant people access who should not have it than occasionally deny the phone's owner access. Okay, so that's some ways we might get some help with testing. What about debugging? Well, I have a program now and I have a basic test suite. I want to be able to run the test suite in my debugger so I can better understand why tests fail. As I showed before, today's debuggers are not helpful with debugging inference. If I set a breakpoint around the call to train face model, I might get to step into the code for whatever ML inference framework I'm using, but that doesn't actually tell me anything about the relationship between my base model, my training data, and the failing example. What I need instead is a new kind of breakpoint and a new kind of debugger, one that can help me to understand the probabilistic phenomenon of correct and incorrect predictions, or even the execution of these statistically defined functions. What I want is to be able to define a breakpoint that will activate when there's a misprediction, which I've represented here with a crossed out P. And then I want my IDE to be data aware and make data visible to me when I'm trying to debug. So let's imagine a scenario where I'm running my tests and they fail on this picture of me. In this scenario, I should be allowed to access my phone, but the classifier says otherwise. So my breakpoint should activate and I should see the failing example in context. I shouldn't see the long list of model weights represented in a human interpretable form. And then I should be able to step into this and I should see how the data flow through the program. And eventually, when I'm bottoming out here, I should get a new kind of UI element that we don't currently have, some sort of prediction debugger. And it should give us at least two kinds of information. Information about the model's confidence in its predictions. Seems I'm right on the bubble. And I should also be able to see similar examples from my training set, giving me some insight in how the model is perceiving my face. It seems that the model has learned to attend to features like beardiness and pale skin and big noses, and perhaps I'd investigate the theory that sunglasses are the problem. It doesn't know enough about those. It's hard to say with this information alone, so a good prediction debugger would let us explore our model's behavior more deeply to see the learned features that exist in the trained model and their provenance in our data sets. At a high level, it might let me filter data in different ways. By exploring the data that are most implicated by mispredictions, I could develop theories about what's going on, what's going wrong, iterate on my training data, and so forth. Now, to be clear, I don't want to give you the impression that I think simple visualizations and intuitions are enough. There's quite a lot of research in HCI and in machine learning about how to create much more powerful tools than that to help developers to quickly discover why they get the predictions that they do and figure out what to do about them. But unfortunately, research in that area, that intersection of HCI and machine learning, has not been integrated into the world of dev tools, nor has it really been drawn on in computing education research. So I'm thinking of older work like K.R. Patel's dissertation work, for which Amy was a collaborator. Gestalt, which is the tool he built 15 years ago now, allowed developers to click on particular kinds of misclassifications and confusion matrices, see examples of those misclassifications in their data sets, and then trace the causes of misclassifications back to things like mislabeled data. You fast forward a decade and you see work like Fred Homan's doctoral research, which won the Chi Best Dissertation Award. It took this approach much further, allowing developers to see the learned features that are activated by particular examples, trace those features' provenance back to the regions of training data that are most strongly associated with the activation of those learned features, and see the strength of those activations and the intersections between the joint probabilistic activation of those learned features. So with tools like this, we can find out answers to questions like, why wasn't my face differentiable from Seth Rogen's? But for that to happen, we need to do translational research to bring methods like these from HCI and ML into the programming tools that developers use, so that these are debugger features, not standalone applications. We need agents that can support these kinds of analyses, that can interpret these kinds of representations, develop theories for developers to investigate, and be aids for developers trying to come up with and investigate theories that they're generating. I firmly believe that we need editors and agents like this to support the future of creating hybrid programs, but we absolutely need to bring tools like this into computing education, because otherwise, how are students going to understand hybrid programs? Very briefly, I just want to note that some of the same ways that my hypothetical IDE helped me with creating and testing my face authentication program are also relevant to things like programming with prompts. As before, I'd want the editor to point out things like the lack of test coverage. And like before, I'd like to be able to auto-generate tests based on whatever examples I've given, such as this particular call. My agentic tool should be able to generalize from the ways I've invoked functions to generate tests. And then when that particular test inevitably fails, because there's a Paris, France, and there's also a Paris, Texas, and each of those locales use a different unit for temperature, I want my agentic editor to help me fix the program. It should be smart enough to summarize the root causes of test failures and propose changes that would address them, keeping me in the loop so that I can edit these proposed plans, but not necessarily needing to generate them from scratch every time. I think there are so many interesting research opportunities nested inside the work we would need to do to create the kind of future I'm describing here. So for example, given a program like this one, how well can we automatically glean checkable requirements that we could use to synthesize tests? How can we make IDEs and agents in them converse with developers to elicit additional information that would support creating more robust programs like this, and even potentially formally verify parts of them across the distributed system of the local program and the remote LLM? And of course, there's the really big question, the one all of us ought to care about, which is, assume this existed. How do people learn to program in that universe? What pedagogies help them to become skilled creators of hybrid programs in this HAISE world? The central concept I'm arguing for is one in which AI agents and people work together, symbiotically supporting each other's deepening understandings of the problems to be solved and the solutions to those problems. And I've presented a couple examples to show how the recursive structure of HAISE could support building, testing, and debugging hybrid programs. Hybrid programs, as I said, are increasingly ubiquitous, but right now they're effectively ignored in SE pedagogy and in computing education research. So HAISE is shaped by, but in turn reshapes this coin, forcing us to reconceptualize what programs are, what we want our programming tools to do, and what it means to practice software engineering. And given these changing A, B, and C, we need to transform what it means to learn and teach software engineering and do these in a reciprocal way. I'm not saying figure out software engineering, then figure out education. I'm saying figure them out together. I want us to undertake formative interventions for HAISE that begin with the kind of work that Leo and Dan have done, but take it further, right? It's not just about programming with AI or learning to program with AI. It must also be about learning to engineer hybrid programs with AI. That's the core concept I'm arguing for. HAISE is the idea that AI systems can increasingly be our collaborators, our thought partners, and our reflective tools as we do the difficult work about reasoning about ever more complex and ever more hybrid software. This HAISE concept demands new programming tools, ones that unify data management and code management, but they also demand new computing pedagogies that are anchored in what it means to be a good software engineer with these kinds of tools. There are many obstacles to this HAISE vision and the vision of HAISE education. Like, we don't yet know how people learn to get good at HAISE. So how do we even study that when it doesn't even exist? Right? There's a recursive challenge there. But this problem is not unique to HAISE. We still have many open questions about how people get good at programming as it existed 20 years. And that hasn't stopped us from innovating in this space. And I don't think it should stop us now. The hybrid view of programs that I've presented requires us to deeply rethink what we do in our introductory courses and throughout our academic programs. As ambitious as work like Porter's and Segaro's is, it doesn't yet contend with the changing nature of programs, only the changing nature of programming tools. Inventing educational experiences where students learn to engineer hybrid programs through HAISE will require us to very deeply rethink the curriculum. And faculty need to come together across subspecialty boundaries to make this happen. I've met too many people who are comfortable teaching introductory programming as it has existed for decades and who are reluctant to experiment with AI. They're comfortable claiming that they teach the programming basics because those are the fundamentals that will allow students to succeed later. But I don't think that's true. As I said before, programs are molecules. If you're just teaching about one kind of atom, you don't get to see that many kinds of molecules. It's a very limiting and it's an unrealistic representation of programs as they exist today. So I don't know how we bring all of our colleagues along, but I think we need to figure out how. I also think, by and large, computing educators and computing education researchers don't do enough tool building, and that's partly because we don't do enough to reward that kind of tool building. There are exceptions, people like Neil, people like Barb Erickson, people like Maddie Tidri. I think all of us need to lean into this area and not just follow along with industry's technical innovations. So rather than reacting to and adapting pedagogy to whatever new tools get shipped out of San Mateo, let's be leaders in inventing new tools that embody concepts for software engineering and for learning that we think are powerful. If we do this, then many good things become possible. We can directly challenge the hypester narratives of our own obsolescence. We can help new graduates to become more skilled software engineers, more like today's senior developers. We can develop a generation of software engineers with more pervasive experience with software testing, including for hybrid programs, which is very rare today. And finally, we can break down silos between technical areas. I want to live in a world where the HCI and ML innovations that are happening all the time, and as I showed, have been happening for 20 years, empower software developers and learners sooner. And I want to be in a world where programmers and ML engineers take joint responsibility for model quality, including creating data sets that can be used to integrate bias measurement into software test suites. But today's divisions of labor, which are enforced by the differential capabilities of the different tools used by different specialties, prevent that kind of joint responsibility taking. By working toward this HAISE vision around hybrid programs, we necessarily will have to de-silo these technical areas and fuse software engineering and ML engineering in the emergent future. So that's what I have to say. I hope I've succeeded in communicating not only what some of our current contradictions are, but provided some frameworks we can use to analyze them and work through them. I've proposed a novel concept, HAISE, and tried to illustrate for you what it would look like within future processes of software engineering to make use of possible future programming tools. There are many things I don't know, like how do we do any of this? And this is just my view. A formative intervention needs to be multi-voiced. It needs to be shaped by you, by other educators, by students, and other stakeholders. So this is an incomplete starting point. Regardless, I hope I've provoked you to want to work toward expansive transformations of what software engineering should be, including developing new concepts for what programs, programming tools, and programming are and should be, and for what it could be like to learn to be a software engineer in a hazy world. Thank you for listening to this talk, and many thanks to the Koli organizers for inviting me.